Low level gang, welcome back to another video. Today we're taking another look at embedded Rust. In this video we'll be creating our own project from scratch and writing Rust that compiles down and runs on an Arduino, the Atmega 328P in particular. Learning how to use Rust in an embedded environment has been such a fun adventure, but so far we've only explored the example code that other people have included with their hardware abstraction layers. In this video today, we'll be writing our own code ourselves and going a little deeper into specifically what each line does. Hit subscribe to follow along with us on our embedded Rust journey. Also, leave a comment below and let me know what you'd like to see next. Okay, so to start this video out, first we need to install the toolchains that will allow the Rust runtime and the Rust toolchain to compile our code down to Arduino code. The way we do that is we install sudo apt install gcc avr. The Arduino is based on an AVR processor, so we have to have the GCC toolchain that can compile C code for Rust down to AVR. Okay, once we have that toolchain on our computer, we are now able to create the package that we will be using to maintain our code, our dependencies, our targets, and things like that. So we're going to do cargo new Rust Arduino blink. That will create an application in the form of a folder at this location. And we can cd into that and look at the files that it's made for us. It'll make two files, the first being cargo.toml. That'll maintain the list of dependencies and different rules that we run on our project when we build and release it. And then the source folder, which will have our basic main.rs, which is where our source code will go for our project. So what we're going to do is we are going to call Sublime on this folder to open up our project, and we need to actually add the dependency of the AVR Hall. So someone actually for us, just like in the previous video, has made a hardware abstraction layer for the Arduino. Hardware abstraction layers produce an API for us to write against that does not directly interface with the hardware to give us a safer abstraction for touching the peripherals of a device. So that location is actually right here. It's github.com/rahix/avr hall. We are going to add that as a dependency to our cargo file. And the way we do that is we make a new dependency. We say dependencies.arduino hall. And we will say that the git location of that dependency is https://www.github.com/rahix/avr hall. And we need to actually specify what revision are we going to depend on. So we are going to depend on revision, the git commit right here. So 92D450C. 92D450C. Cool. And then another base dependency that you want to add when you write any kind of Rust project that's embedded is you want to add the panic halt handler. This basically incorporates a panic halt function that gets put into your code so that if the board were to panic, it knows what to do. So now that we've had those dependencies added to our code, I'm going to increase the font size a little bit for you right there. We can now do cargo update, and it should, nope. Before we do the update though, let's make sure we pull the www off of GitHub. It actually does not like that in the package manager. So we'll do cargo update here, and it'll pull down the AVR Hall and the other crates for this project into our local working dependency. So now what we need to do is tell the project that we want to compile code for the AVR target. The way we're going to actually have to do that is by making a special folder called .cargo. And in that special folder, we will sublime a file called config.toml. So this file is a place where you can actually specify the target of your project. So in our build run, right, this is the rule for when we're building the code. We want to say that the target of our project is a specific JSON file that will describe how to compile our code. So AVR Atmega 328P. .json, and you're now saying, okay, where does this JSON file come from? The producer of this hall actually created a JSON file for us in the AVR specs. We can just go ahead and download this file. I'm going to copy and steal it real quick. All this file really does is describe what is the architecture, what is the CPU type, what is the layout of the different file types or data formats, right? How big is a 16-bit value, stuff like that, and then what flags to feed the GCC. So we're going to take this, we're going to steal it, and we are going to call it a new file, and it's going to go into here. We're going to call it avr atmega 328p.json. Cool. So now when we build our code, it says the target is this file and this file is this, and it tells the Rust runtime how to compile. Also here in our config file, we have to include this code here that says that this is an unstable build and it uses the core library as a standard library. Remove the addition key. It's also another minor Rust-ism. If you don't have the addition key set to the right time, it won't know how to compile it. Awesome. So now we got that all set up. The final thing we need to do is we need to set the build chain of Rust to a particular version that is compatible with the Rust AVR runtime, or the Hall rather. So the way we'll do that is we are going to use rust up and override the toolchain to be set to a particular nightly distribution. Yeah, we need to say rust up override set nightly 2021 0107. If we don't do this, the Rust build will actually not really work. We won't be able to produce any code because it won't know how to invoke the AVR toolchain if we're not using this version of the Rust toolchain. That's my only major complaint about Rust so far, is that there's little niche things like that you need to know that if you don't know, you literally just can't run code. Finally, we need to change our main source code and add a couple of things to make it Rust embedded compliant, right? So what we're going to do is add a few things to get this into embedded mode. The first is going to be no standard. No standard puts the Rust compiler into embedded mode, meaning it doesn't bring the whole lib Rust, it brings only lib core, and it allows us to write code for a kernel, for firmware, just smaller applications. Next, what we're going to do is say no main. No main just means it's not going to expect that we use a main function. Instead, we can specify the entry point manually based on the specifications of the hardware abstraction layer. We need to then create a panic handler for the processor to look for and use if it were to panic. So we're going to say use from the core library and the panic sublibrary, the panic info struct. And we're going to define a panic handler. Handler, spelling is hard. And we will call it function panic. It will take in an object named info that is of panic info type. It will return never. So this is not null. This is not nothing. This is the never type. It means that this function is not allowed to return, and it checks for that at compile time by basically saying, if you're able to get to line 9, you're wrong. So the way we avoid that is we put it into an infinite loop. So if we panic, infinite loop. Not a very good panic, but it'll do. Next, we have to tell the Arduino Hall, hey, this is the entry point to our code. We do that by saying Arduino Hall, which is the name of our library. Remember, Arduino Hall. This is your entry point. And we can name this function main. It's kind of counterintuitive given that we said no main. We can name it function potato. It really doesn't matter, but we'll say function main for now. And same as before, because this is an embedded system with an entry point, this is meant to return never. And again, that is checked at compile time by making sure we can't get to the line 14 here. And we enable that by doing an infinite loop. And then one final thing we have to do with our Arduino Hall as well is say that the features that we want to extract from the Hall is that for the Arduino Uno. If we don't do that, it won't know what features to expose in the Hall when we're compiling our code. So we'll go ahead and put that in there real quick, and then we will go ahead and build our code. Okay, cool. So now we have in the target folder, target AVR Mega debug, a Rust Arduino Blink, elf file that is an atmel AVR 8-bit elf with debug info in it, not stripped. So pretty cool. Again, obviously though, this code doesn't do anything. We don't care about this code. So we are going to add some functionality that will make our LED blink. Okay, so this is pretty standard for any hardware abstraction layer that is written in Rust to extract away peripherals from a device. We're going to say let peripherals, holy shit, English is hard. Peripherals, there we go. Equal Arduino Hall. Within the Arduino Hall, it's pretty standard for there to be a peripherals structure. And we are going to take that and unwrap it. Cool, so now we have a peripherals structure that we can use that gives us access to all the peripherals of the Arduino chip that we're on, the AVR chip. Then within the peripherals, there's actually a macro that gives us access to the individual pins. And that macro is called Arduino Hall, called pins. And it's a macro, so we use exclamation point. And we feed it the peripherals structure that we already have. Now we have a pins structure that gives us access to the individual pins on the chip and allows us to do things with those pins. Then next we do let there be a mutable LED that comes from pins. Its name is D13. That is a digital 13 pin where the LED lives on the board. And we're going to turn that into an input pin, or excuse me, turn that into an output pin. Cool, so now we have this LED structure that is a reference into the pin structure that controls digital 13 as an output. And then all we have to do is call led.toggle and then use the Arduino Hall to give us a delay of 1000. And because it's a toggle, this will turn on and off, and we'll just run this in an infinite loop and not violating the never return type of main. So we'll move this over to the right a little bit, and we will do the same thing. We will do cargo build, and there we go. Cool, so now our target AVR at mega debug has the Rust Arduino blink.elf. Let's actually see how big this is. I'm kind of curious. Pretty big, man, 600K. So what we're gonna do now is we have to actually flash it to the Arduino. How do we do that? So first, I've got my Arduino plugged into my computer, and you can see it's here on dev TTY ACM0, I believe. Yep. So we're gonna use the Arduino dude command. Arduino dude. We're going to use the AVR dude command, which is the programmer that allows us to send ELF files over various programmers to an Arduino to put your code onto that device. So AVR dude takes a few commands, a few different arguments. I'm going to actually specify them right now. First, you put down AVR dude. The second that you're going to do is the type of processor that you're programming. So you're programming an M328P. The next we're going to do is we are flashing using an Arduino, because Arduino has a baked-in bootloader already written to the EEPROM, so you don't need to do anything special there. We're going to do the port, which is dev TTY ACM0. Pull this up here. The baud rate is 115/200, pretty standard. And then we are going to write to the flash a writable section, and it's going to be this ELF. Cool. So again, using AVR dude, which is this type. It's an Arduino programmer. We're putting it on this port, and this is the baud rate, and we're going to write to the flash area a writable section, which comes from this ELF. Hit enter. There we go. Now it's writing it to the board, and boom, we verified it, and we have the code running safely on our Arduino, flashing every 1 second. Guys, I hope you learned something here. I hope you understand that Rust does, in fact, run on everything. All you have to do is either write or find a hardware abstraction layer, use that hardware abstraction layer to expose peripherals, and then burn that new binary to a board. If you like this video, or if you learned something at all, do me a favor, hit like, hit subscribe, leave a comment, and I'll see you guys in the next embedded adventure. Take care, y'all.